All right. So yesterday we talked about all the different special line segments and triangles. So that included perpendicular bisectors of the sides, angle bisectors, altitudes, which are line segments that go from a vertex to the opposite side perpendicularly, and medians, which go from a vertex to the midpoint of the opposite side. And basically, the bottom line is you just need to be able to identify each of those things and know what they're called. Any questions about that stuff? Remember, if you have really organized notes, it's not really anything you need to memorize. You can always just refer to that, okay? So maybe make a table or something like that so that you can refer to it really easily if you need to on a test or a quiz, okay? All right, so today we're going to talk about points of concurrency. So this might be an unfamiliar word to you, so let me just define it. 3 or more lines are called concurrent if they intersect in a single point, okay? So 3 or more lines are called concurrent if they intersect in a single point. It's 3 or more because if you have 2 lines, they always intersect in a single point if they intersect at all, right? But you could have 3 lines that intersect at different points, right? This point, by the way, this single point where they intersect, this is called the point of concurrency. Okay, so if you have a line here, and a line there, and a line there, these would be concurrent lines, okay? That point is called the point of concurrency. Okay? It's easy to envision 3 non-concurrent lines. Just picture like a triangle kind of, right? Something like that. These are not concurrent lines. Okay? So there's some important facts that have to do with the special line segments that we talked about yesterday, okay? So here they are. Okay, so first of all, the 3 perpendicular bisectors of the sides of a triangle are concurrent. The 3 perpendicular bisectors of the sides of any triangle are concurrent. They intersect in a single point. And the point of concurrency has a special name. The point of concurrency is called the circumcenter. I'll say that too fast, it'll come out like circumcision or something like that. That's something different. So the circumcenter is the point of concurrency of the three perpendicular bisectors of a triangle. Okay, so if I draw a picture here, suppose I have this triangle right here. And I draw, I'm just going to eyeball it. I'm not going to do like a formal construction, although I could. I mean, I know how to construct perpendicular bisectors. I'm not going to do that. I'm just going to eyeball it, okay? So if I do the perpendicular bisector of this side, it would be like something like that. All right? If I do the perpendicular bisector of this side, there's the midpoint, it would be like something like that. And if I do the third one, it's going to go through the same point. So it would be something like this. Okay, that point right there is called the circumcenter of the triangle. Now it's possible that the circumcenter could actually be outside the triangle itself. And that's the case if it's an obtuse triangle. Like for example, I could have a triangle that's shaped like this. And if I do these three perpendicular bisectors, the perpendicular bisector of this side would look like this kind of, right? The perpendicular bisector of this side would be like that. And you can see they're intersecting outside the triangle. If I do the third one, it's going to be like this. So in this case, you can see the circumcenter is outside the triangle. Or you could even have a situation in which the circumcenter is on the perimeter of the triangle itself, if it's a right triangle. Yeah, sure. So suppose I have a right triangle like this. You can see what's going to happen if I do the perpendicular bisector of this side, it's going to be like a horizontal line segment. If I do the perpendicular bisector of the other leg of this right triangle, it's going to be a vertical line segment, and they're going to intersect right on the hypotenuse. Does that make sense? That would be true? And then the third one, obviously, would go right through the same point. So the circumcenter might be inside the interior of the triangle. It might be outside the triangle entirely, or it might be on the perimeter of the triangle in the case of a right triangle. Okay? In any case, there's an important property of the circumcenter. Okay? Here's the fact, which I think is kind of interesting. The circumcenter is the center of the circumscribed circle around the triangle. So there's a lot of weird words here. So the prefix circum means around. So circumscribed means drawn around. It's like Latin for drawn around. Circumcised means cut around. Yikes. So the prefix circum means around. So when you're talking about the circumscribed circle, you're really talking about the circle that could be drawn around the triangle and actually pass through each of the vertices. So if I look at these pictures that I've drawn here, let me use a different color. I'll use yellow to draw the circumscribed circle, the circle that just barely fits around this triangle. And you can see, if I draw that yellow circle, that black point's actually the center of that circle. It's the center of the circumscribed circle. I didn't really draw it very perfectly. Let me try that one again. That looks a little bit better, I guess. But the same thing goes for all of these situations. Like if I draw this circumscribed circle, it's going to be really big because it's an obtuse triangle. And you can see that black dot is the center of that circle. And if I draw this one, same thing. That black dot's the center of that circle. So that's a really important, kind of interesting property of the intersection point of the perpendicular bisectors, is it's the center of the kind of the smallest circle that fits around the triangle. Okay? Any questions about that? All right, let's go to the next point of concurrency. So this would be like number 2. The angle bisectors, the 3 angle bisectors of a triangle are also concurrent. The 3 angle bisectors of a triangle are concurrent, meaning they intersect in the same point. This point of concurrency also has a special name. Point of concurrency is called the in-center. Okay, so we have the circumcenter, which is the intersection of the perpendicular bisectors, and we have the in-center, which is the intersection of the angle bisectors. So if I draw a picture, there's a triangle right here. If I draw the 3 angle bisectors, so we have this angle bisector, and again, I'm just eyeballing it, these are not exact, just eyeballing it. This angle bisector, and then the 3rd angle bisector, they're all going to intersect in the same point. And that point of intersection is called the in-center. Now, for the circumcenter, there were 3 possibilities, right? It could have been completely within the triangle, it could have been outside the triangle entirely, or it could have been on the perimeter of the triangle. We don't have that problem or whatever with the in-center, because the angle bisectors, if you think about it, they are themselves completely within the triangle, right? So it doesn't make sense that if you have 3 segments or lines that are completely within the triangle, that they're going to somehow intersect outside the triangle. It's just physically impossible, right? So it doesn't matter. I could have had an obtuse triangle like this, and the result would be the same. The intersection point would be inside the triangle. Like I could draw this angle bisector and this angle bisector. You can see already, I don't even really have to draw the 3rd one, right? Because they're all going to intersect in the same point. But I will draw it, and the 3rd one will go right through, and they're all 3 going to intersect inside the triangle. So we don't have that same issue that we had with the circumcenter, where it could be inside or outside or on the triangle. This one's always going to be inside the triangle. So the in-center also has a really important property that's interesting. The in-center of a triangle is the center of the inscribed circle. Okay? So we talked about what circumscribed means. It means drawn around, right? That word scribed means drawn. Like if you think of like old biblical times or something, the scribes were the people who wrote stuff down, right? So circumscribed means drawn around. What do you think inscribed means? Drawn inside, yeah. So if you think about like the biggest circle you could possibly fit inside a triangle, that's going to be the center, that's going to be the in-center's circle. So like if I tried to fit the biggest circle I could in there, the center of it is right there at that black dot. Does that look like it should be that way, right? And if I look at this one, same thing. If I draw the biggest circle I can in here, that's the biggest circle that will fit there, and its center is right at the in-center. Kind of interesting, right? So just on vocabulary, like if I have any polygon inside another polygon or geometric figure, there's that circumscribed, inscribed relationship. So if I have, for example, a square with a circle inside it, okay? This is just a general thing about geometry in general. So if I have a square with a circle inside it like that, okay? I could say that the circle is inscribed in the square. This is a circle inscribed in the square. Or I could say this is a square that's circumscribed around a circle. It's the same relationship, just written a different way. Okay? I could say that the square is circumscribed around the circle. It's just describing the relationship in a different way. It would be like me saying, I am Julia's father, or saying, Julia is my daughter. It's the same relationship, just described a different way, right? That's exactly like this, okay? So the in-center is the center of the inscribed circle, and the circumcenter is the center of the circumscribed circle. Everybody okay so far? It's a little confusing with the vocabulary, but like I said, you have notes, so just organize them well, and there's really nothing to remember. But I'll show you in a couple minutes, like the way I remember these names, because they do get a bit confusing. Okay. Number 3. So what's the third special line segment we talked about yesterday? Altitude. Altitude. Okay, so it turns out the 3 altitudes are also concurrent. Okay, the 3 altitudes of any triangle are concurrent. And yes, you guessed it, their point of concurrency has a special name that involves the word center. Okay, so the 3 altitudes of any triangle are concurrent. The point of concurrency is called the orthocenter. Orthocenter. Does anybody know what the prefix ortho means? Like orthodontics or orthopedics? Or I don't know if you've ever heard the word orthogonal. What's that?
I think bone.
Close. It means straight. So an orthopedist is in charge of like straightening like bones and body structures. Orthodontics is straightening your teeth, right? So ortho means straight. So what does that have to do with altitudes? Well, altitudes are like perpendicular, to the base. So maybe that's where that name came from. I'm not really quite sure, but anyway, a little Latin lesson. Okay, so if by the way, I had to take 4 years of Latin in high school. It was terrible. Anyway, so suppose you have a triangle, okay, and I draw the 3 altitudes of this triangle. So the one here goes straight down to there. This one goes straight down perpendicular to the other side, and this one goes perpendicular straight down to that side. That point right there is called the orthocenter of the triangle. And this is kind of like the circumcenter. It could be outside the triangle completely. Okay, like for example, suppose I have this triangle here, right? Now remember, if it's an obtuse triangle like this, you have to draw an extension of the opposite side, right? So I'd have to extend this side out like this, and then the altitude would be this line segment right there, right? Now this is where it gets a little weird. If I draw this altitude, no problem, it just goes straight to there. But if I draw the altitude from this vertex, I'd have to extend this side. So it would be like from here to there. And you might be like, they don't intersect at all. But they actually, if you extend them, they will, right? You can kind of see where this is going. Like this is going to be extended out this way. This is also going to be extended out that way. And this is going to be extended down this way. And they will all intersect in the same point eventually, if you draw them out. So there's the orthocenter of that obtuse triangle. And if I have a right triangle, where's the orthocenter going to be? Any predictions?
Middle of it.
No?
No?
What do you think? Where's the orthocenter going to be in that triangle?
Somewhere along the center,
Where? Precisely.
the right angle.
Right at the right angle. Because this altitude, good job by the way, this altitude goes from here straight down to there, perpendicularly. This altitude goes from here straight down to there, perpendicularly. You can see where they intersect, right at the right angle. That third altitude goes from the right angle over to this side, but definitely their point of intersection is right at that right angle vertex right there. Does that make sense, that should be that way? Now, the orthocenter doesn't have any cool properties. I'm sorry. It's a little bit of a letdown. It's the black sheep of the family. Doesn't have any cool properties. I'll write that just to make it official, just to make it feel even worse. The orthocenter has no cool properties. Imagine if a parent said that about their kid. I'm sorry, you have no cool properties. That would be crushing. Sorry, orthocenter, I feel for you, bud. All right, so the fourth one, what is the fourth special line segment we talked about yesterday? Medians, yeah, the medians. So what do you think is true about the medians? Well, they're concurrent, definitely, right? And do you think that maybe the point of concurrency has a special name? Yes, it does. Okay, so the three medians of any triangle are concurrent. And the point of concurrency so far? We have the circumcenter, which is the intersection point of the perpendicular bisectors. We have the incenter, which is the intersection point of the angle bisectors. We have the orthocenter, which is the intersection point of the altitudes. And finally, we have, this is called the centroid. Centroid. Okay, so circumcenter, incenter, orthocenter, centroid. Let's draw a picture. So if I have a triangle like this, and I draw the three medians, so the median is going to go from a vertex to the midpoint of the opposite side, like that, right? From a vertex to the midpoint of the opposite side. And from the vertex to the midpoint of the opposite side. That point right there is the centroid. Do you think it's possible for the centroid to be outside the triangle? Probably not. Yeah, I think it's not, because think about it. The median itself is never, no part of the median is ever outside the triangle. So if you have three segments where no part of them is ever outside the triangle, then how would it ever be possible for their intersection point to be outside the triangle? It's just not possible, right? So this can never be outside the triangle. It's always going to be inside. It doesn't matter what type of triangle it is, whether it's a right triangle, an obtuse triangle, or an acute triangle. The centroid is always going to be inside the triangle. And the centroid actually has two cool properties to make up for the ugly brother orthocenter. So here's the facts about the centroid. The first one is that the centroid is the center of gravity of the triangle. Centroid is the center of gravity. Of the triangle. So center of gravity, what that means is you can almost think of it as the center of gravity as like the balancing point. So you can think of it as like if you were to make this triangle out of plywood, okay, like universal thickness plywood, then this would be the point where you could balance that triangle on a stick, and it would hold on there. Okay, so that's another reason why there's no way it could be on the perimeter of the triangle or outside the triangle if it's the balancing point of the triangle. It has to be kind of in the middle of the triangle, right? So that's one important property of the centroid, is it's the center of gravity. Another important property is a more analytical property, and it is this. It says that the distance from the centroid to a vertex is always twice the distance from the centroid to the opposite side. Okay, so that kind of is hard to read by itself, but it's easy to do problems that deal with this. What that means is, if I look at my picture up here, where I have a centroid drawn, it means that if I look at any one median, it's divided into two parts by the centroid, right? There's like a shorter part and a longer part. This longer part is twice as long as that shorter part every time. So this longer part is twice as long as that shorter part. this longer part is twice as long as that shorter part. Does that make sense? So if they told us that this long part right here was 12, then I would know that this has to be 6. Or vice versa, if they told us that this little part right here is 4.5, what would this part up here have to be?
9.
It would have to be 9. Does that make sense? So they could give you either one, either the long part or the short part, and you could find the other part, right? Or they could give us the whole thing. Like if they told us that this whole thing right here is 12, right? You know, it's like, it's split up into thirds, right? This is 2/3 of that, and this is 1/3 of that, right? So this would have to be 2/3 of 12, which is 8, and this would have to be 1/3 of 12, which is 4. So they could give you the short piece of a median, or the long piece of a median, or the whole median, and you can find the other pieces missing there. And that's what the homework's about, actually. Out of all the stuff that I said today, that's what the homework is about, is just that fact. Okay, because that's all Delta Math had about it. But the bottom line is you have to know all these words too. You have to know that the intersection of the perpendicular bisectors is called the circumcenter, and that it's the center of the circle that you could draw around the triangle. The in-center is the intersection of the angle bisectors, and it's the center of the circle you could draw inside the triangle. The orthocenter is the intersection of the altitudes. It doesn't really have anything special about it. And finally, the centroid is the intersection of the medians, and it's the center of gravity of the triangle, and it has this interesting property about the lengths of the pieces of each median. Okay, so it's kind of a lot. This is like the longest notes we've done all year. Yeah. But any questions about that stuff? Okay, so that's all I got for today. The homework's on Delta Math, and it's just called points of concurrency. But like I said, it only relates to the centroid and that relationship between the lengths. Okay? I'm going to stop recording.